with ME627. Today we will begin with the damped Mathieu equation. Now why are we doing this? Well, I hope if you remember, we started with something like Q dot is equal to F of Q T. We thought of Q dot equals F of Q as a special case. We thought of F of Q star equals 0. We thought of Q is equal to Q star plus xi for local analysis. We found eigenvalues. We ended up with xi dot is equal to A xi. We found eigenvalues. Then we looked at real part of lambda greater than 0, that means unstable. Real part of lambda less than 0 for all lambda, that means stable. Real part of lambda equal to 0, that means borderline, center, right? Neutrally stable. This, when it is of the form plus minus I omega, this leads to oscillations, and that is why we went to x double dot plus x equals epsilon times something as a perturbation of the harmonic oscillator. We studied that, and then we are also studying this one. That's the Mathieu equation, and which is a special case of the Hill equation. Okay, so these are some of the things we have studied. For the Mathieu equation, via Hill's equation and Floquet theory, we found that on the parameter plane there are stability boundaries that look like this, etc., and all of this is stable. And these are unstable. Etc. Okay, so we saw that. But this is the undamped case. What happens if it is damped? So as you have seen in a picture that I showed briefly from somewhere else, if we have some damping, then the stability boundary becomes like this, and over here maybe like this, and so on. That's what damping does. Okay, so this little region of instability may just become a stable region because of the damping. But now we are going to think about this stability boundary, because it is obvious to ask what happens to the Mathieu equation when. So let us say 2c x dot plus delta plus epsilon cos t times x equals 0. Now for this problem there is actually a nice trick, and that trick is most easily shown in Maple because it will save time. So let me go to Maple now, and here what I will do is I will say dE is equal to the derivative of x of t with respect to t twice plus 2 times c. The 2 is just for algebraic simplicity. You can absorb it into the c if you like, it doesn't matter. So that's the damping term, plus delta plus epsilon times cos t times x of t. In this problem, we don't treat epsilon as small, right? So it's just a parameter. That thing is going to be 0. This is the damped Mathieu equation. So the trick is we say xs is x of t is equal to exp minus c times t times y of t. Okay, so this is the substitution I will make here. So I'll say dEA is equal to expand, substitute xs in dE. Okay, so that's what I've got there, and I have to solve for d square y dt square, and so I'll say dEB is equal to solve dEA for that, and what I will do is I will do Control V here also and minus, so that once again this thing is 0. Okay, so that's the differential equation. Okay, and I hope you realize that something quite interesting has happened, which is that the damping term has gone away. And so here is y double dot, and here is y. There is a delta minus c square, and there is an epsilon cos t. So let us go back here. So if we try x is equal to, x is equal to e to the power minus ct times y, then we get y double dot plus delta minus c square plus epsilon cos t times y equals 0. Okay, so now this is just the Mathieu equation in disguise, right? Where I had delta, now I have delta minus c square. There is a horizontal shift to the old stability picture, this stability picture. There's just going to be a horizontal shift, right? So previously where I had stability at delta equals 1/4, now I have that same place at delta minus c square equals 1/4. Okay, however, remember that the stability boundary for y is not the stability boundary for x. For y, we need growth like, y needs growth like e to the ct to compensate. Because of that, this growth will compensate this decay, compensate for this decay, and then beyond that x will grow. So if you remember, our stability result was that for the Hill's equation solution, eigenvalues have unit magnitude. So either they are on the complex circle or they are on the stability boundary, which is here or here, and I'll mark them differently. So one is solid and one is hollow. So these are two different situations. Or if I mark them in blue, then one here and one here. Or if I mark with a circle, one here and one here. Okay, so you see that for y to be growing, I have to have a real eigenvalue that is bigger than 1 in magnitude. Then this will come here. If the solution is of time period capital T, then e to the power minus, the eigenvalue required is e to the power c capital T. That's the eigenvalue required, which is greater than 1 for c greater than 0. Okay, so this is where we need to be. And then what will happen is, due to this multiplication, this exponential contraction, it will be just balanced on the point of growth. Okay, so this means that we have to go into the unstable region. That is why we are going into the unstable region, and this curve is like this. On this curve, remember the unstable solutions that we have studied earlier. From that or from this idea, you will see that the final eigenvalue is, see, Floquet theory applies even to this system, so there are eigenvalues, and so you know that the final eigenvalue is going to be 1, and on this there is going to be a periodic solution. So now an interesting question, because we have done so many computations in this course, an interesting question is, can we compute this curve? So let's try to do that with MATLAB. It is a reasonable thing. In some courses people would not be doing that, but over here we will do it because you know how to do it. Okay, so first of all we need the Mathieu equation, and here is the Mathieu equation. Mathieu equation, let me remove this. Over here I will need a global parameter, which is the alpha parameter. So over here let me say alpha. Okay, and delta. Then delta will be set, no, let me say delta 1, and then I will say delta equals delta 1 and epsilon equals alpha. And now I have my Mathieu equation, except there is a damping which I have to specify, of course. So I'll specify the damping here. Let us say the damping is 0.3. Okay, so that's the damping, 2c, so 2 times c. So over here I will put minus 2 times c times, maybe I'll make it a bit smaller. I don't know what I'm going to end up with, x of 2. So this is the damped Mathieu equation. I will be setting the parameters delta and epsilon from outside, but other than that, this is the damped Mathieu equation. There's no problem. Okay, now I'll come here and I will have my ODE solution accuracy. I will come here and I will say delta 1, get rid of the rest. Okay, then I will specify my integration accuracy, and now what I will do is, what are the equations I'm solving for, right? So I have, so let's go back here and try to figure out our solution strategy, right? So what we are doing now is seeking periodic solutions. So what is the period? Let us say 4 pi. Then both cases are covered. Okay. Now we need to know delta and epsilon. C is given. And we need to know x of 0, x dot of 0. Okay. So we need to know 4 things, so that when we integrate to 4 pi, we get x of 4 pi equals x of 0. We get x dot of 4 pi equals x dot of 0. So we have 2 equations, right? This is the parameter. This is what needs to be done. We need 3 equations, right? So what I'm trying to say is that think of these 3 axes, right? So I have x, we can't really draw it like that, but I need these 3 things. Epsilon is a parameter. Okay, so I need to know 4 things, but I want a solution curve. So now epsilon is a parameter. If epsilon is a parameter, then I need 3 equations here, and the third equation will be obtained from the fact that it's a linear equation, you see. So if x is a periodic solution, then 2x is a periodic solution, 0.63x is a periodic solution, etc. All of them are periodic solutions, and so we will have x0 square plus x dot 0 square equals 1. Maybe positive, maybe negative, we don't know. So these are the three equations that we will have. Epsilon will be the one parameter. These are the inputs. I hope that is clear. With this thought, let us go back to MATLAB now, and what we will say is, let's see, delta 1 equals x1, okay, x0 equals x2, xd0 is equal to x3, okay, and alpha is going to become epsilon in the solution. There is no problem. And then what we will do is we will say ty equals ODE45 Mathieu 0 4 times pi, what initial condition? X naught x d naught OP. Okay, so I've got that initial condition now, and now I have to set up my equation. So I will say y is equal to y end transpose minus x naught x d naught. So those two things need to be 0, and then I will say y is also equal to y and then x naught square plus x d naught square minus 1. So that's got to be 0. Okay, very good. I think that will work. Now I come here and I have to look at my continuation curve and remind myself of how that went, right? So I have to go to continuation, and in the continuation what I need is a big X, and the function name of course is junk because we are using that all the time. So I need a big X and I need an alpha. Okay, so let's come here and let us say global alpha big X. Okay, now let's go here to this curve, right? So this point is 1/4. Let me move a little bit here and let us say this is 0.18. Let us say this is 0.18. Epsilon, my alpha, is going to be a little bit higher than what it was earlier, right? So this was about 0.05. I'll set 0.06. I'll try for alpha. Okay, so I'll come here and I will say alpha equals 0.06. My guess is 0.18. Okay, so then let me say Newton. Let me look at Newton and make sure that I don't have a very tight error tolerance, because then I'll get into trouble. 10 to the minus 7 minus 11. Okay, so let's make this 10 to the minus 9. Let's make this 10 to the minus 5. That should be all right. And then let's come here and let us try 0.18 and then 0.7 and 0.7. I have no idea what I'm doing, but we will see. Z has to be assigned, so Z needs to be assigned. This is Z. Let's see how that works. So it has given me an answer. Okay, so then what I have to do is I have to say big X is equal to this has to be answer. Okay, so it's given me an answer. All right, now let me change epsilon, very, very small. So let me say alpha equals 0.058, very small change. Okay, and then let me say a equals answer just for the heck of it. That's the answer, right? A equals answer. So then I go y equals Newton junk y a a. So I got another answer, and then let me say big X equals this. This is what we have done earlier, you know, so we are just doing that now. And now let me do continuation, and not that many points, you know, let's do 100 points. This is actually a different delta, but that's okay, we'll get some answers. Maybe I need not have done that many. If I stop it, I'll still get an answer. So let us say I've got 58 points. That's not very bad. Okay, so now let us look at these points. These 58 points, you see, this was delta, so it is on the negative side. It doesn't matter. That's delta. This is epsilon. Okay, so on the horizontal axis. So now the plot will just be like this: big X1, that's the delta part, big X4. You see, so that is where it is close to 0. This is one of those stability curves. And what I will do here is now I will say xx is equal to big X just to store it. And I will also say hold on. Okay. Now, the other thing I will do is I will say big X is equal to that. We'll get rid of it. Alpha equals 0.06. And then I will try Newton only with this. I will try 1 and 0. It's having trouble. It will give me some other answer. It gave me the same answer. I don't like that answer. Let's try let us try to remember. We had delta was 1/4 plus minus epsilon by 2, right? So if epsilon is 0.06, then 0.22 is a good value of delta. So let's try that first. Okay, so 0.22. Alpha is 0.06. Let us try 0.22. It is giving me the same answer. It is giving me the answer I don't want, unfortunately. But let's do something else. Let us try alpha equals 1. Well, 0.4. We'll just get a different answer. We'll see what we get. Okay. Okay, that's a different answer. Okay, so now let's see what that curve looks like. All right, so that's one, and then alpha equals 0.39 or 38, and then there's another one, so that's another one, and then now we have two, and let us say some 40 points. I see now why that initial guess was not working so well, is because the damping is rather large, but it's okay. We have another solution now. We'll see what we get. Let us give it a few seconds, and then we will look at the graph, and then we will move to the next topic. I hope you noticed something over here. Previously we were solving equations where the functions were explicitly written in terms of polynomials. Here we are evaluating a function, and the evaluation of the function involves ODE solution. But I hope you see that in principle there is no real problem. And okay, we've got our answer here. So let's plot this one in red. And then if we look at the graph, you see, so this was one solution, this is the other solution. From 0.25 it's jumped up quite a bit. Okay, this graph, if I continue, it will go over there. I hope you can see that this is the graph that will go like this. I hope you can follow my cursor, and this is the graph of the instability branch that would have started from here at 0.25, but because of damping it has popped up like this. Then there will be other graphs over here, for example at this point, whatever that point is, so over here, let us say at this point here, it will, there is a periodic solution. That is what we have done by construction. So for example, if I look at the very last point, there is a periodic solution. Okay, so let's look at that. So let us now say hold off, get rid of it. Let us say big X, all rows end. Okay, good. And now let us say this is my initial condition, this is alpha, this is delta. So I'll come here, I'll say format long, and then answer, and you see this is my delta now. So let me go to my Mathieu equation, get rid of comment. Okay, so let me come here and say delta equals that, and epsilon equals that, and let me say x0 equals that. So that's my initial condition, and now this is just routine Mathieu equation with damping, right? No problem. And so we come here and I say T y equals, no, that's no good, T y equals ODE 45 Mathieu 0 4 times pi x0 OP. Okay, plot T y. Both x and x dot will be plotted, and it should be a perfectly periodic solution. So it starts here and it goes there and comes back here. This starts at some value and comes back to exactly the same place. Okay, how do I know that? I can do the following. I say hold on, and then I can plot it again, only I can say plus 4 times pi, right? And then I can plot it using magenta, and then you will see that it is working. So you see that it is perfectly periodic. Okay, so there is a periodic solution on the stability boundary. How do I know it's the stability boundary? If I increase epsilon a little bit, it will become unstable. So plus 0.05. Now let me start it with the same initial condition, but go for a few more periods and hold off and plot. And you see it is growing. It's unstable, right? Similarly, if I go minus 0.05, then I am in the stable region. And now it is decaying. So that is the solution we found is on the stability from boundary. We found that curve of delta and epsilon. Let me remind you again. Plot this curve here. This is a point on this is a curve on the stability boundary. Okay, so that's the end of this lecture. Thank you.